Everybody, so my name is Michael Gonzalez, and I'm a computer engineering major at Santa Barbara City College.
I'm Brenda Perez, and I'm a civil engineering major at San Joaquin Delta College.
I'm Alyssa Barbosa, and I'm a marine biology major at Santa Barbara City College.
And I'm Jeffrey Nunez, and I'm a computer engineering major currently attending Hancock College.
So our research this week was all about analyzing a new search algorithm for ocean searches. I'm sure most of you, if not all of you, know about the Malaysia Airlines flight MH370. It was a plane that had 239 people and has been missing since March 8th. Since then, there have been continuous searches, but none have been successful. So what this tells us is that we need a better algorithm to get better results. In this picture, up here you can see Indonesia. This is Australia, the white spaces. And in between them, you have the Indian Ocean and all its complex surface currents. Flight MH370 is believed to have landed in this area. But with all these complex currents, how can we maximize our efficiency while we're searching?
We can use a search algorithm. What a search algorithm is a mathematical and data-based path that a search agent could follow. A search agent could be anything from an autonomous underwater vehicle to a plane. And once they know a certain path they could follow, it could take them to their target.
So some applications for a search algorithm are, ocean-based disasters, like previously mentioned, airplane wrecks and shipwrecks as well. Another interesting application is locating the path of oil spills and where they will be going in the future in order to maximize cleanup. And so, like a really good algorithm can save time, money, and even lives.
So our goal this week was to compare different search algorithms, find the most efficient one among them, and then apply it to ocean-based disasters.
So in order to do this, we used software created in MATLAB by the research team. And to make simulations, we changed different variables, such as the search agent velocity, the search agent being a UAV or an airplane, and also its detection radius, like how close it has to be to a target in order to find it.
One of the algorithms we studied was the Lawnmower Method. As you can see here, in any static motion, the Lawnmower Method goes along its way as any other, as you would be mowing the lawn. But for ocean-based disasters, we applied this simple fluid flow to all our lawnmower simulations. Before showing you one of the lawnmower simulations we ran in our lab software, as Alyssa mentioned, I'd like to point out what you are about to see. So the search agents are the crosses, which could be, like we've been saying, AUV or planes. The path they leave behind are represented by the green and the red dots. And the baby blue circles, those are the targets. Once they are detected by the crosses, they turn purple. Here in the animation, you can see the crosses go up. Once they reach the top, they will turn a certain amount, that distance that they were given previously, and they go down. So you can notice from this that they are covering very much white spaces where the targets aren't really at, and this wastes a lot of time and takes too much time to find the targets.
So the second algorithm that we looked at this week is being developed by Ecomesic's research group, and they call it the Dynamical Spectral Multiscale Coverage Algorithm, or DSMC. So DSMC works by using the data on the distribution of targets in the search area. In this first image, you see the initial distribution for one of our trials. So the red areas indicate the most likely places to find the targets, and blue means less, and outside there's no chance of finding targets at you. So just like with the Lawnmower Method search simulation we ran, we use the same fluid flow model, and as you can see over time, the distribution, the density of the targets is spread out due to the ocean currents. And by the end of the 20-second simulation, the density has spread out into this complex pattern. And now these three images are showing the same exact simulation But now we're just looking at the agents and the area that they can cover. So this is the initial distribution of the agents. It's randomized in our simulation, but this time it happened to be practically right on top of the target density distribution. But as you can see, over time, the targets will be hunted out by the agents using the algorithm. And by the end of the 20-second simulation, the area covered by the targets is mostly exactly covered by the agents due to the efficiency of the algorithm. But how does this algorithm work, and why is it so efficient? Why do we believe it is more efficient than other algorithms could be? Well, it's dynamic because everything in the simulation is moving. The area covered by the targets is also moving, and the algorithm keeps track of all the area that has been covered by the agents and calculates where to go in order to not repeat searching areas and to head directly towards the most dense regions to find the most targets in the short amount of time as possible. Additionally, the algorithm also calculates and determines when it's best for the agents to sweep in small, short wavelength patterns or to sweep wider areas so they can cover more ground and get to the higher destinations more quickly and maybe get out of the way of the areas they've already seen. And this is the example of our agents moving in the patterns. So with these two methods and other parts of the algorithm, areas can be searched more efficiently. And that's what we were testing to see whether it was more efficient than not. In this simulation, you can see right away that the agents are moving in a fairly complex pattern, and right away a lot of these targets have been found already, and they mostly avoid the white spaces and head directly towards the targets.
So to compare the efficiency between our two methods, we have to look at how many targets are remaining, which is our y-axis, over a period of time, our x-axis. And so what we did is we ran many trials, took the results, and averaged them. Here you're looking at the lawnmower results, and you can see that after a period of 20 seconds, the lawnmower method has about 48 targets left. It's not bad. But now when we look at the Dsmc method, we can see that in the same amount of time, it has about 20 targets left. That's better. And if we also notice, at 5 seconds, the lawnmower method has found about 40 targets, so it has 60 left to still discover or notice. The Dsmc method, at the same 5 seconds, only has 40 left. So it's clear that Dsmc is much better because it finds more targets in less time.
So, in conclusion, this week we found out that the Dsmc method, search algorithm method, is more efficient and works much better than the lawnmower method. So we hope to apply this in the future to other ocean-based disasters like airplanes, as airplane wreckages, as we've been saying. And we hope that this algorithm will be taken into consideration when other wreckage need to be found.
So now that we know that the Dsmc method is more efficient, when we look at this picture of the Indian Ocean and all its complex currents, this blue region represents where flight MH370 is believed to have landed. And so in a situation like this, the general routine to find the area you want to look in is discovered, or what you have to do is look back at the position information received by radar either from the plane or from the ground. You can also look back at the planned flight route or speak with eyewitnesses. And in this animation, you can see that the effects of the Indian Ocean surface currents, what they are on our search area. Applying the lawnmower method here would not be very effective because it doesn't take these changes into account. However, the Dsmc method does, and therefore is much more appropriate.
So in the future, the MESIG lab hopes to continue improving the Dsmc algorithm even more in order to better model real-life situations.
Before opening up to any questions, we'd all like to thank our great mentor, Sophie, as well as our advisor, Igor. Thank you very much. We'd like to thank all the directors and advisors too from the program, Maria, Jens, Christophes, and also our resident assistants that are always with us and telling us, great motivation skills. Also UCSB, the Messick Research Group, and the Jan Ken Foundation. Thank you.